So the next topic is this binomial distribution. It's very similar, actually, the normal distribution. In fact, it turns out maybe in class we'll do a little experiment. We can find that the binomial distribution actually ends up looking very similar to the normal distribution. But what is first of all, what is the binomial distribution? Well, this is the case where we have something that has two possible outcomes for every trial, and then we just want to count. This is a discrete distribution, right? Discrete distribution. So that means count, right? That means we're going to count how many times a certain occurrence would happen, right? So here, for example, if we're inspecting finished goods, they can be classified as either good or bad, right? So we could also, anytime we have only two possible outcomes. So for example, our M&Ms keep coming up. We could say it could either be plain or peanut, right? If I have this big jar of M&Ms and there's only one of two possibilities, plain or peanut, that would be a binomial distribution. Well, that would be sort of what we call, yes, a binomial distribution. In general, though, we have to figure out what would be a success, right? And then we count the number of successes. So count the number of successes, and that is what we call a binomial distribution, the count of number of successes. So there could be, if I had this jar of M&Ms, and 50 times I pulled one M&M out at a time, and then put that one back in. I would count how many times I had a success, and I would define a success before I started. Maybe I would say the peanut M&Ms would be a success, and then at the end I could say, well, this is how many I had, right? So that number is actually distributed, right? If this is randomly generated, so that's what we have. So we have to know the probability of success. We're going to call that P. Right? And we assume that P is constant from trial to trial. That means that I'm not pulling out an M&M and popping it in my mouth. It's actually the exact same probability every single time we do this. Right? So the M&M example gets sort of not so fun, but in a minute we're going to look at some other examples. All right, so what's next? 3 important assumptions for the binomial distribution. We have n independent trials. N independent trials. So we're going to see this n, this little n, right? This n again, n independent trials. So this is just the number of times I try something. So back to the M&Ms. Say if I pulled out, I wanted to pull out 10 M&Ms, the N would be 10, right? I pulled out 10 different times. Every time I tried it, I would be an experiment. So how many times did I experiment with something? There can only be 2 possible outcomes, and the probability of success has to be constant from trial to trial. So that's what we just talked about. All right, so this is just like the normal distribution has this. We can represent it as a formula. This looks amazing. So this n with this x underneath it actually ends up looking like this with these exclamation marks, which means they're really excited. It's like n x. No, that's not what it means. These are n factorials. So a factorial, if you remember what a factorial means, you probably remember this, but it means something like, let's say if I have a 4 factorial, remember what that means? That means like 4 times 3 times 2 times 1, right? So we just multiply everything all the way down to 1. We don't care too much about that, but that's what these factorials mean. So we got a bunch of factorials, and then we're raising things to the power of x, 1 minus p, n minus, we don't really care. So if we did care, though, we'd have to figure out, again, how to take an inverse of this and kind of figure out, we could create a chart and figure out the probability of all these things. Instead, you guessed it, we're just going to let Excel figure this out for us. And it's really easy. Once we figure out any of these dist functions, right, norm dist, binom dist, they're all almost exactly the same. So we can figure one out, then we can just kind of figure out the rest. There's others that we're not going to cover in this class, but they're very similar. In this case, we have x, right, so this is what we want to try. So we'd say, I know some probability, p, and I go run an experiment n times, right, and then maybe I get some x, right? And then I say, what's the probability of that happening? That's really what we're asking here. What's the probability of that happening? If there's only one of 2 things, right? And the p has to be the percentage of successes, right? And then this I is the final thing. It can be either 0 or 1. If it's 0, then we have an exact. So this is a discrete distribution, right, as opposed to a continuous distribution, which means that we're allowed to just say, what's the probability of our x exactly equaling something? We're allowed to say that. Where we couldn't do that with continuous distributions. Or we can let I equal 1, which then gives us back to this idea that we're going to look at the left side of something. Okay? So, side note, But for a binomial distribution, we find the mean of n times p. This is going to make a lot of sense in just a second. Or the standard deviation looks like this: n times p times 1 minus p. So that's just, we just believe that. Although this is very intuitive, and we'll see why in just a second. All right, so here is a problem. In a population of sales invoices, there's this sales voice population out there living and breathing in their own universe. 5% of them don't have shipping documents attached. What a shame. If an auditor takes a random sample of 50 invoices, so you can think there's this little population of sales invoices, they're just living in their little town, and then this big giant this big auditor, who's sort of like this big god, comes and pulls them out randomly. I could make a video out of this. Maybe I should. 50 invoices. What's the probability that exactly 3 will have missing shipping documents? So that's our first question. What's the probability that there will be at most 2? And what's the probability that 5 or more will have missing documents? And then finally this question, what is the expected number of invoices with missing documents? So let's just work through these one at a time, and we're just gonna do it with the binomial dist function. All right, so the first one, first of all, we can write binomial dist functions in shorthand just like we did before. We use a b this time. Hard to remember these, comma n, comma p, where n is the number of trials and p is the probability. So in this case, what's our n? What's the number of trials? Well, we pulled 50, right? So we tried it 50 times. And what's our probability? Our probability is 5%. It's right here, 5%. 0.05. That's how we'd write it. So this is a shorthand for a binomial distribution with n trials with a percent of successes of 5%. So in this case, a success would be a missing sales invoice. So when we say success, it doesn't have to be good. A success can be bad. We just define whatever the success is, all right? It doesn't really matter. All right, so what's the first question asking? Well, it's asking the probability that x equals 3, exactly 3, given a binomial distribution with 50 trials, probability of 0.05. All right, so how do we do this? We just use this binomial dist function. Whoops, binomial dist function. And what do we put in here? We put comma, let's make sure we write this down, this 3, right? That's what we want to try. We want to see what the probability of 3 happening is. So this is what we put it in first. How many trials we got in there? 50, comma, what's our probability? 0.05, comma, and then we put in 0 instead of 1 because we want to know the exact, right? Exactly 3, which is allowed in this case. So this guy equals, I think it's 21.99%. You should go try that, but that's what I got. All right, let's do the next one. Probability this time, what's probability that there is at most 2? What does at most mean? At most means less than 2, right? Less than or equal to. At most 2 is the biggest that's allowed. It can be less than 2. All right, so x then less than or equal to 2 given binomial distribution with 50, comma, 0.05. And all right, I kind of wrote this wrong, but this is exactly the same thing, right? Binomial dist, comma, or no, bracket 2, right? 2 is what we're after this time. 2, comma 50, comma 0.05, and then instead of 0 this time we say comma 1, right? And the difference is here we want to find the exact. That's what if we put a 0 in here, or we could write false in here, or we could write, for 1 we could write true, does the same thing. And this is because we want a cumulative, right? We want it to add up, less than 2, right? So if we were to draw this, again, here's our arrow, less than or equal to 2, all right? That's good. So what's the next one? It's probably a 5 or more. 5 or more. So probability, let's change colors. Probability that x is greater than 5 or more, greater than or equal to 5, given we have a binomial distribution of 50 trials, 0.05 probability of success. Well, this one's a little trickier, right? So this is greater than. So just like before, we can't actually just figure out greater than. But we could figure out less than or equal to 4. Right? And that should give us exactly the same thing. So remember, in this case, think of how many we could possibly have. Well, what could x possibly be? Well, x could be 0. It could be less than 0. It could be 1. It could be 2. It could be 3. It could be 4. It could be 5. In fact, it could go for a while here, but it can't be smaller than 0. We can have negative these things. And we can't have 1.5, right? There's nothing in between. That makes sense, right? So you have to have exactly some exact whole number of invoices missing documents. We can't have some fraction of. So what we want in this question is everything bigger than this, right? Everything bigger than this. But what the binomial dist function gives us is this part, right? However, we know that this entirety here, everything all the way until, who knows, until 50. This can go to 50, right? Can't get any bigger than 50 because 50 is the number of trials. All of that equals 1, right? If we just sum the probability, not x, but the probabilities of all of those, or what we like to call the f of x's, right? Of all of those, that equals 1. So this is like the 20th time I've said this. You sum these all up, they equal 1. So knowing that, then we can just say, well, if we can figure this part out, subtract it from 1, it gives us this part, right? So that's exactly what we're going to do. This is just like what we did before with the norm dist. So it's just 1 minus binomial dist, comma, but instead of 5, let's look at my picture. I actually want to look at 4, right? Because if I do 5, it'll include 5. Well, I want 5 to be included down here. So if I include 4, it'll find everything smaller than 4. Subtract 1 from that, which is what I got here, 1 minus that. Then I should be good to go. So 4, comma, 50, comma, 0.05, comma, 1, right? Because I want the cumulative. I want it all. And that'll give us, that's the right answer right there. And I think, actually I didn't do this before, the answer here is 10.36. And then I actually do have an answer for the one above too. It equals 54.05%. So we'll get some practice doing this in class the next time around too, but hopefully this helps you understand. So the last part, what is the expected number of invoices with missing documents? This one, we can actually just think about this intuitively. So if I have 50 documents, and from the past somewhere, I figured out that 5% have missing, or are expected to have missing shipping documents. Those are the outcasts of our population. So of these 50, how many are expected to have missing? Well, 5% of those, right? That's it. That's all that's going, what's expected. So what is that? 50 times 0.05. Let's try that. 50 times 0.05. Which is, well, I don't know. 10% of 50 is 5. So this must be 2.5. Half of 10%. So I figured that out. So we expect that 2.5 of these should be missing. Well, we know that half, there's no such thing as a half of these. But that's what we say. We would call this an expected value. Expected value. Which we also call the mean. Right? That's the same thing. This is actually the average number of missing things. And why do I say that? Well, it is. But look at this. We actually figured this out earlier, or it was written here. Mu for binomial distribution equals n times 2. That's just what we did, right? We did 50 times 0.05. So this mu is completely intuitive. This is just the average or the expected number of ones that are missing documents. This guy is not quite as intuitive, but it's simple. We can just plug it in and go what's going on. Again, the same interpretation, though, that this is the standard deviation. It's the average deviation away from this mean. So we could plug this in and figure that out. So it's not too hard. We're not going to do it, but that's okay. We're taking a break. All right, it's almost bedtime, and I'm going to get kicked out of the office shortly. So let's finish up these notes. We're almost done. So we just finished with this binomial distribution. We're going to do several of these in class, so hopefully we get a little bit more practice doing this next class period.